This is part 2 in the series of tearing apart a QD-OLED TV. Part 1, if you haven't checked it out yet, I encourage you to do that. We're going to dive right through the eye of the microscope here and look at some quantum dot pixels. Here the red and the green subpixels both contain quantum dots. The blue does not. The color from the blue will come from the OLED backlight. You can see here the abnormal pixel arrangement that others have mentioned. The green is a little larger than the red and the blue. And in theory, both the red and the green contain the quantum dots that give us that color. We're looking at white light transmission through these pixels right now, but we can also light these up with a UV flashlight and see the fluorescence from the quantum dots. So now we're looking at the red and green fluorescence from the QDs. And back to white light. These pixels should be about 0.3 millimeters total, and it turns out they're very close. About 315 for each pixel. The green is a little larger than the red and the blue. And I've got another image here that I was able to capture of just the quantum dot layers alone. And we're going to touch on this weird shape and kind of honeycomb structure that exists later in the video. The simple pixel here is just blue OLED exciting green and red quantum dots. And the blue subpixel has no quantum dots. So this is maybe a structure you're familiar with if you know a little bit about QD-OLED. It's actually a little more complex than that, which is what I'm going to show as I tear into this TV and get some real analysis on all the different parts. So here I've tried to scribe the glass and break a nice square off of this TV. I was unsuccessful, partly due to the plastic film on the surface, which I'll mention more about later. But that was okay. I was still able to use this part and many others like it with jagged edges to take a look at the inside of the device here. I also took my hand at trying to get a cleaner cut using a Dremel tool, which, while it ended up giving me a nice cut, it was a little bit more messy. That's why I've got the vacuum out here to keep the dust down, because I am cutting through a few layers of glass as I do this. But it does give you a nice cut, and I'm able to look at the different parts of the screen by doing this. So here you can see from the top down, the QD-OLED backplane that kind of looks silver, that's been separated from what I'll call the QD front plane and then a plastic film on the back. The OLED backplane is about 0.5 millimeter thick. The QD front plane is a little bit thicker, but that includes the plastic film. The majority of this thickness is actually glass. The QD color converter and the blue OLED are a layer right at the interface there between the two substrates, and the total thickness is only about 1.1 millimeters. Here you can see that in a microscope. So a lot of people commented during the first video about the reflection handling, so I thought I'd take a closer look at that and remove this plastic film off the front of the TV that presumably is some sort of anti-reflection film. And when I do this, I test this out a few different ways. I think the easiest way to look at it, which I show here in the video, is by using a UV flashlight, and I'm shining that down on part of the film that I've removed, where I've removed the film, where it's just glass, and then part where the film is still intact. And you can see how, even with an iPhone camera, you can see how the reflection handling is very different, where the film was and where the film still is. Now, this is just with white light in this picture, and then we'll also look at this with blue light, because that's important. We get a lot of blue light from our LED lights in our life. And then this is with UV light. And what's interesting here is you can start to see the red emission from the quantum dots. The red emission from the quantum dots comes from the excitation of that UV light. Now, this is a very strong UV source that's causing only very weak quantum dot emission, whether it's through the plastic or not. But when I use the blue excitation source, a blue LED, I actually see no quantum dot emission at all. So that tells me that it's unlikely that we're going to get just regular room light exciting this material. Here's a piece of the TV from the front and from the back. You can see the OLED separated from the QLED here. If I shine a UV light on it, you can see the bright colors from the quantum dots. A lot of damage there too. From the front, if I shine the light on it, you can see that you don't see any colors coming back. So there's some sort of filter preventing quantum dot excitation from the front here. But if I put the flashlight behind it, you can see it really lights up. So from the back, it can be excited and we see the colors coming through. From the front, it cannot. So from the front, if I do that, looking back at the back, you can see not much in the way of quantum dot emission because this UV light is being filtered. If I flip it over, lots of emission. So clearly there's something preventing quantum dot excitation from the front of the TV. Now we're going to move on to the OLED exciting the quantum dots from the back. I'd like to be able to answer these two questions, what the native blue emission looks like, and if there's any green present as well. It's difficult to measure this OLED emission directly because I've now damaged the TV, but I have a backup plan. I can measure the OLED backlight excitation of green and red quantum dots, which I did in video 1, and I can also measure the excitation of the quantum dots with a UV flashlight, and we can compare those two cases to see the difference. I'm not the first one to propose that there might be a green layer here. This is something that's been rumored in this industry. If we look at the green from the front of screen measurement, this is with the OLED backlight, you can see it's a little bit more broad than the QD panel only with UV excitation. In the red case, they're both very similar. So it's possible that this broadened spectrum that I measure at the front of screen is due to the green OLED that's contributing to the color we see in the green. Now we'll look at the OLED device that's driving this whole quantum dot layer. And we don't learn a whole lot about the device here other than getting some nice pictures of it, one under white light, one under UV light. I'm going to go back to the quantum dot layer again now, and you can see I've scraped off this layer off of this film, and I'm not sure what it is exactly yet. So I've removed this coating. I don't think it's actually intended to be an optical layer. And we're going to look at if this is conductive to determine if it's part of the OLED device that's come along for the ride when these devices separated. And so you can see the part that's shining with quantum dots here. That should be all polymer and not conductive. So I'm testing this with my voltmeter. Turns out, yes, in fact, that is not conductive. And if we move over then to the other part where the film is still intact, this unknown film, it does appear to be at least somewhat conductive. And so I think this is an electrode from the OLED device stack that has separated with the quantum dot layer. So that must have been the weakest link in the device. And now if we scrape a little further, we can see something really interesting. There's a lot of blue color filter, is what I'll call this, in areas that are not just the blue pixel. So I'm a little bit surprised by this. I thought the blue color filter would only exist in the blue pixels and not everywhere else under what's called black matrix, but it appears it's spread everywhere. So that's an interesting and unexpected finding. And then if we look at the green and red color filters, we can really point them out in these two comparisons, one with white light, one with UV light. In the white light graphic, all the pixels portray their own color, especially the ones that just have the color filter kind of hanging off the edge of the sample. But in UV light, only the quantum dots light up, the color filters do nothing, and they just turn black. And so you can see the comparison here that really demonstrates the green and red color filters. So I've now built up this simplified pixel to be more accurate, I think. It's got blue and green OLED, I believe, exciting the quantum dots. A little bit of that green is going to come through in the green pixel, but not in the red and blue because of the color filters. And then you'll have this ambient light blocking layer at the top to prevent excitation from room light. And finally, we'll look at the quantum dot layers only. This piece happened to separate when I broke the pieces off the TV, and you can see this interesting sort of honeycomb structure holding things together. This appears to be the red, green, and blue pixel, subpixels, so the red and green are the quantum dots. And presumably this is where these materials are inkjet printed into this type of honeycomb lattice, if you will, to hold the quantum dots in place, to keep them in each of their respective subpixel locations. Here the same device is lit up with a UV flashlight. You can really see the green and red emission. And I'd love to hear more about what you guys want to see in part 3. I still have this TV, and I am continuing to study pieces of it and learn more about it. I appreciate you watching, and let me know if there's other things you want to hear about.